All right. Good afternoon, physics class. Let's get into this here. Let's get that peanut butter scalar time. Peanut butter vector time. All right, you know about scalars and vectors. We've done some business with this going back in the time. You did this in refi. Scalars you see on the left, vectors you see on the right. They look pretty similar. Yeah, one's mass, one's acceleration. Left time, right speed. Left work, right distance or displacement. However, there's something missing here. You see, what we look at here is kind of our short version, our cheap version, or we just want to run numbers in the calculator version. In reality, vectors get a little indication here. Let's see, let's give it a little hat, a little hat, a little hat, acceleration, velocity, displacement, force, electric field strength. There are plenty others. You can't put a hat on any of these scalars. What's the hat there for? Well, the hat's telling us that there's more to this than just 5 meters per second squared or 10 meters per second. In fact, there's something called a direction. And what that means is if you actually are to talk about acceleration, you can't just say how much. You have to say which way. And so here's an answer. How about 5 meters per second squared at 36.9 degrees counterclockwise of due right? Well, you could figure that out. Here's a velocity. Due left. Here's a displacement at 55 degrees south of west. Sure. Here's a force toward the top of the page, counterclockwise 27 degrees from that. And finally, here's an electric field strength straight out of the page. So the thing to recognize is that though in refi, we frequently just neglected the fact that vectors are in fact unique and different. Here in CoFi, we will not do that. You have to pay attention to these things. So let's just do a little more vector talk down here. We're going to lay on that. Ooh, that's interesting. We're going to lean on that acceleration of 5 meters per second squared at 36.9 degrees, counterclockwise of due right for a little while. In fact, I sketched that out down here. Oh, there it is. Here it is. And you may say, well, wait a minute. What are all those happy faces there for? Let's just clarify. This arrow does a very nice job of representing this acceleration. Why? Why does that arrow represent 5? Because we say it does. That's it. You'd make a scale. You'd say maybe a half a centimeter is 1 meter per second squared. So then 2.5 centimeters would be 5 meters per second squared. Something along those lines. And that angle, well, if we were to draw due right over here, due right is something like this. This is tipped up 36.9 degrees counterclockwise of due right. All right, so let's move due right out of here because we already know about due right. Now, why are all the happy faces here? Because you should know that this acceleration is acting on an object, and it can be acting. We don't actually know where the object is. The object could be here, or over here, or over here, or over here, over here, over here, or over here. It doesn't really matter where the object is. So it's important to recognize that frequently with our vectors, it does not actually matter where the arrow is located, just that the arrow has a length and a direction. And that tells you about the acceleration. There's nothing about this arrow that's showing us, oh, well, the acceleration like begins here and ends here. That's completely wrong. It's got nothing to do with it. This arrow is talking about an acceleration that's existing at a moment, an instantaneous acceleration of some object somewhere. Now, the problem may tell you where it is, but don't get caught up on location. Basically, we can draw these wherever we want to represent that acceleration. Good, next page. All right. Thing we got to do in order to actually make sense of our vectors is establish a frame of reference. Now, look at these two rulers here. I had already preset this up. There we go. If you notice, there's a triangle here. The base is 4. The height is 3. This is a 3, 4. The hypotenuse is 5. A 3, 4, 5 triangle. And if you do tangent of this angle right here, then the opposite is 3. The adjacent is 4. Theta comes out to inverse tan of 0.75, about 36.9 degrees. So I point that out because for much of what we're going to do, we are going to just assume this 3, 4, 5 triangle to keep it simple. Okay, cool. Now, establishing a frame of reference, you must first set some sort of origin. So let's say we take this right here, bring him down here. There's our 5 meters per second squared at 36.9 degrees, counterclockwise of due right. So typically what we do is we introduce an x-axis and we introduce a y-axis. And as I said before, it does not actually matter where you put this, but it is convenient to draw your arrow beginning at the origin, or the tail of the arrow at the origin of these axes that you make up. This is a frame of reference. So don't get too excited about what does that mean. We're just choosing a way to talk about this arrow. So this is our y-axis, this is our x-axis, and as long as someone else has axes that look like this, we can talk about that 5 meters per second squared at that angle. All right, so this is a pretty straightforward thing. Now, what you're going to want to do is sketch your vector, make axes, and establish positive. So just come over here for yourself. Put a little up is positive, right is positive, or positive y, positive x, we're going to call positive. That's going to matter for our course, so you're going to want to do that. Just to extend beyond this for a moment, we actually have 3 dimensions. This is a 2D up here. If you tip this a little bit, here's your up, here's your to the side, and Z is like coming out of the paper. Now we will do this in our course. Not every unit focuses on it, but the way we draw the Z axis, or the coming out of the page or going into the page axis, is sometimes you put a little dot. A dot would represent a vector coming out of the page, and similarly an X would represent a vector going into the page. We'll worry about that a little later, but basically that comes from the idea that a proper arrow actually has feathers on the tail. And so if an arrow were coming toward you, like you see here out of the page, you would see the point of the arrow, that's the dot. If an arrow were going away from you, or a vector is pointing away from you, the feathers are staggered around that shaft, and so you would see an X. You would see the feathers on the back of the arrow. All right, here's just a picture of a plane. You can see this with boats. 3 different axes, the roll axis, the pitch axis, so different ways you can rotate this plane, and the yaw axis, kind of your vertical axis there. All right, let's go. So, big thing in vectors is the resultant. Why do we care about the resultant? Because it's the net effect. It's the net effect. It's this cartoon over here. Which way did he go, George? So if you have a boat in a river, let's say, here's your boat. Let's say there's a river over here. Here's the water. Okay. Maybe it's an interesting day. Lots of complicated little wave patterns in there. Anyway, if the boat is directed up and to the right, that darker purple arrow, then its engines are pushing it. It's experiencing a thrust up in that direction. However, perhaps the wave motion, that's sort of lighter, that lavender, perhaps the wave motion or the wind motion is up and to the left, as you see there. By the way, that arrow also conveniently, I just made that also a 3, 4, 5 triangle, so that everything's simple to work with on this. So the resultant is basically which way is the boat going to go. That's what we're trying to figure out. So many times you have multiple vectors, maybe multiple sources of velocity, multiple forces creating multiple accelerations, and you need to put them together and say, well, all right, that's great, but which way is the boat actually going to go? And so the way we do that is we find the resultant. Last year, you did what we called head to tail or tip to tail. So if you notice up top, this looked like this. You could pick up either one of the vectors and put it so that you now have them oriented head to tail or tip to tail. On the left here, we move the lavender to the tip of the purple. On the right, we move the purple, which was down here, to the tip of the lavender. Now, the way we teach it is you find the naked tail. That's the start. You call circle the start, circle the start. You find follow the arrows, naked head, that's X the finish, X the finish. And then draw a resultant directly from the circle to the X. And what do you have? Boom. There's the resultant velocity. Over here, notice we went in different order, but you get the same exact result. Let me move the X out of the way so you can see it. Same exact result. So which way did he go, George? That way. Notice the same. There was also a parallelogram method that you may have done. In the parallelogram method, you had your original vectors coming off the object. We sometimes call this clock hands. And you just complete the parallelogram. So we repeated the purple vector up and to the left. We repeated the lavender up and to the right. You see the parallelogram begins on the boat and ends up here. And the resultant runs from the start to the finish. And what do you know? It is the exact same resultant as it was previously, obviously. Okay? So those are the methods you know. So the resultant's important because it basically tells us the net effect. And these are the ways you were working on the resultant in the past. Now, quantifying the resultant. So this is all well and good. You know, sketching these is nice. But what if we need to know exactly how far, or how long rather, and which way? So what if we need to know the exact final velocity or the exact acceleration? Well, we need to quantify that resultant. How do we do that? One method is an extremely accurate sketch. We might even call it an accurate sketch. Of course, that is not so easy to do because it depends on your art skills. And there tends to be some sort of error there when you're measuring and drawing. So what you could do here is you could draw this very carefully, and then you could either measure this angle and the length of that red arrow there, that's that resultant. We had it on the other page as well. I think we had it bright green. And then you can figure out the magnitude and the direction. You could also do this with, let's not do all that. You could also do this with this angle here. In fact, you could do it with whatever angle you want, but you're going to refer to those axes. Another way to do this is with geometry. So you could do the law of cosines and the law of sines. Now, this works. It's hard to do, though, when you start adding more vectors to the situation. It becomes difficult to scale up, so to speak. So you're dealing with 2 in the resultant. And then if there's a third vector, well, now the resultant and the third vector make a new resultant. And so it gets pretty messy. It works, though. In fact, I show it to you right here. You know, if you're really interested in proving this, do it yourself or pause the video and look this over. But basically, the numbers work out easily in this one because I made both the purple and the lavender 5, and they're both at 36.9 to a certain axis. So angle C, you figure this out. The resultant C up here, the red C, turns out to be, the red C, turns out to be 7.07 meters per second squared about. And its angle relative to the x-axis, so that's this angle right here, turns out to be 81.9 degrees. So it's good to keep this in our mind, that the actual resultant here, using the law of cosines and the law of sines, and you need them both, comes out to a little over 7. It's a square root of 50 at 81.9 degrees, counterclockwise to that x-axis, which is the traditional way we give angles in math class. All right, there's another way to quantify resultants, and that's going to components. That's going to components. So these are the same 2 vectors we've been working with. I'm going to call this one A1, and we'll call that angle 1. And then this one over here, we'll call A2, and that'll be angle 2. Notice, those angles are relative to different axes. And it may be like that. You don't get to choose in every problem. In some problems, they'll tell you, well, this is how we want it. So here, notice, A1 has an X and a Y component, looks like that. A2, an X and a Y component, looks like that. All right, now you may say, all right, I've done this before, but what are we actually talking about here? So what we're actually talking about here is A2X, this one, and A2Y in combination have the same net effect, have the same resultant as A2. So if you have A2X and A2Y both acting, or you have just A2 acting at that angle, they're indistinguishable. You end up with the same resultant. So what we're making here is an alternate representation. You know, in a very real way, you can say, instead of writing the number 5, you know, we're going to write the number, in normal math, we would write, let's say, 2 plus 3. Instead of 5, you could say 2 plus 3. Of course, these two mean the same thing. What's the difference? We are doing vector algebra, very basic, but we are adding vectors. And so the rules are a little different, and we'll check them out in just a moment. All right, how do you figure out a2x and a2y? How do you figure out a1x and a1y? Well, that's just a SOHCAHTOA. Keep in mind, we are dealing with the angles that are listed there. So I go over the lavender and the purple here at the same time. But notice, a2x is down here. That's this one. That is the same as if it were up here. So we drew it down here, but it's the same as if it were up there. And relative to theta 2, that is the opposite. And so a2x is a2 sine theta 2. a2y, that's the same as if this were over here. So that's an adjacent to theta 2. a2y is a2 cosine theta 2. And of course, you see with the a1, same sort of business. Now, what are these little bars here? What are these little vertical bars? Well, you know, those are absolute value. Those actually represent, this means magnitude. Those represent magnitude in physics class. And just like in math, absolute value, we don't care if it's positive or negative once you use that. It works the same way in physics. It pulls away any sort of directionality. It just gives you the magnitude. So what this is saying is the length of a2x is the length of the resultant times the sine of that angle. So we are only getting lengths here. We are only getting magnitudes. Now, of course, these lengths represent accelerations. So we're actually only getting magnitudes of acceleration here. Okay? And of course, the numbers, if you run them, come out to 3 and 4. These are 3, 4, 5 triangles, obviously. All right, now let's go and make use of this. How can we represent with components? Let's go. Here's the same picture we had, and now we know from the math we just did that this one has a length of 4, this one has a length of 3. We knew this one was 5. Over here, this one has a length of 3, this one has a length of 4, this one has a length of 5. So now we know that. We figured that out on the previous page. All right, let's go down over here. One way we can write this, remember before I said in normal math, you say 5 is the same thing as like 2 plus 3. You can write these, they mean the same thing. Well, when we're adding vectors, vectors add as a drawing, here as you see. Vectors add as making a resultant. That's what vector addition is. You have to put them head to tail, like we did back over here. This is vector addition. You make them head to tail, circle the start, X to finish, find the resultant. It's not the same thing as 3 plus 4 equals 7. Here you actually have to add the arrows. So that's what vector addition is, and that's what we're doing over here. Let's come on down. One way to write these is called component notation. So notice, over here, we got the resultant, we have the X component, we have the Y component. So this line represents vector addition. a2x we know is a 3, a2y we know is a 4, a2 is a 5. So obviously 3 plus 4 doesn't equal 5 because we're adding vectors here. So this is really the line. 5 meters per second squared at 36.9 degrees counterclockwise of up is 3 meters per second squared in the negative x direction plus 4 meters per second squared in the positive y direction. Of course, you can do the same thing with the purple, and you end up with a very similar result. And then right here is how we actually find the resultant. Now remember, we figured out the resultant with the law of cosines and law of sines before, so this should not be alien to us. All right, how does this work? Well, the resultant is actually going to be a combination of this one and this one. So what do you get when you combine right here 3 in the negative x direction and right here 4 in the positive y direction, or positive x direction, excuse me? You end up with 1 in the positive x direction. And what do you get when you combine 4 in the positive y with 3 in the positive y? You end up with 7 in the positive y. Now, how do you get the resultant? Very simple. You need its magnitude and its direction. So you should always draw these things. I'm going to re-sketch it right here. We're ending up with 1 in the positive x direction and 7 in the positive y direction. And so the resultant is going to be this. Okay, fine. How would we figure out the length of that resultant? It's a junky drawing, but this is a right triangle. This is a squared plus b squared is c squared, which is exactly what we do right here. And it comes out to 7.07 as expected. And then, when you need to find the angle relative to that x-axis, it's just tangent, opposite over adjacent, and it comes out to 81.9 degrees, just as it did before. Okay? All right, let's go on down here. I'm going to show you 2 other notations. Why? Because they're convenient. Up here, we said all this business. We wrote out all this. Another way we can write this is with bracket notation. 5 meters per second squared at 36.9 degrees counterclockwise of up, that's the lavender, is the same thing as this bracket notation. -3, 4. So we put the x and then we put the y. And those little brackets there tell you we're talking about a vector, and that's the x component, and that's the y component. We also do it with the purple, and it's a 4, 3. Now here's the cool thing about bracket notation. We just did it up here too. Is all you got to do is add the 2 different components. -3 plus 4 is +1. 4 plus 3 is 7. In bracket notation, that resultant vector is 1 in the x. Sketch a little. 7 in the y. There's the resultant. So you can actually write this bracket notation. If you had to solve this, this sketch does it for you. 1 and 7. A squared plus b squared equals c squared. Tan theta is opposite over adjacent. So the sketch is really key. All right, let's roll down here to the last one, IJK notation. Now, sometimes people get a little excited, like, what is this IJK? Don't worry. Don't worry, let me show it to you. Over here, you call this your x-axis, you call this your y-axis. Sometimes what we do is we take what we call a unit vector. Vector just means it's got an arrowhead, it's got a direction. Here's another unit vector. So what do we mean, unit vector? Let me bring this guy to the front so it's in front of the axis here. Okay. Unit vector means it is 1 unit long. The fact that it's 1 unit long means it doesn't, if you use it next to anything, it doesn't change the number. So here's a little, it's a neat way and sometimes a useful way to represent vectors. You'll see. Same picture we had up top. Okay? Check this out. Instead of writing 5 meters squared, blah, 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 before we said 3 in the negative x and 4 in the positive y, we might write 3 meters per second squared in the negative I and 4 meters per second squared in the positive k. You see those right here. If we're going to call the x-axis the I-axis, we have the I unit vector on the x-axis, and yes, we always use I for x, and then the y-axis, we're going to have the j unit vector. Yes, we always use, no, I don't need all that. We always use the letter j for the y-axis. And as you might be able to figure, we use the letter k for the z-axis. So this gets into multiplication a little bit, but don't worry, just roll with it for now. You'll see this enough that it'll become familiar. All right, so another way to write the same exact 5 meters per second squared at 36.9 degrees counterclockwise of up is to say it's moving, or it's -3 in the I hat direction. So that means you're going -3 this way, that's this one, and 4 in the j hat direction, that's this one. The purple vector is 4 in the I hat direction, that's this one, and 3 in the j hat, that's this one. The I hat and the j hat tell you which way. It's just another way to say in the x or in the y. Just another way to say it, and there are reasons for it, but get used to it now to keep it simple. And the nice thing about it is when you do the math, you just add them up. -3 and 4 gives you 1 in the I hat. 4 and 3 gives you 7 in the j hat. And of course, it draws out the same thing as we've been drawing. And so you're going to get the same result. All right. Functional expression. Let me show you this real quick. They might ask you for the resultant acceleration. In fact, they may just say, find the acceleration. You can't be lazy like refi, like, oh, let me just figure out the amount, the magnitude. No, they want it. That means they want direction with it too, most likely. AX, AY, and they want the resultant acceleration at a time. Huh, that's interesting. Well, notice both of these are expressions of time. So it's not a crazy thing. If you have something that's pushing on your object and it changes how hard it pushes with time, there you go. You have a time-dependent acceleration. Anyway, we got to go to basics. And if there's anything you listen to today, let it be this. Step 1, draw your axes. I don't like those axes. Make them straight. Here we go. Step 1. Is it dashed? Good. Draw your axes. There's one. There's the other one. Step 2. Define positive. I'm going to call this way and this way positive. Step 3. Sketch. Now in this case, it's a little awkward to sketch, but it'll do. 5t plus 3. So you don't actually know what the acceleration of the x is, but you know it's always positive x. So if t is 0, it's 3. If t is 5, it's 28. So whatever, it's just this way. This is your ax arrow. Ay is negative 3t, so you know that that's going to be always negative, so in the y direction, so maybe it's this one, ay. Now we like to draw these head to tail, and they're looking for the resultant, so personally I say, all right, make them head to tail, and the resultant is circle the start, x the finish. There is your resultant acceleration. Why is this important to do? Because it makes it glaringly obvious how to get the answer. Clearly this is Pythagorean's theorem. Clearly this is going to be, a is going to be the square root of ax squared plus ay squared. Now this is actually going to give you the length or the magnitude of a. Now there are two ways to go about this. Plug in all the variables here and then plug in the time, or plug in the time first. In this case, it's mathematically much easier to plug in the time first. So if the time is 3, 5 times 3 up here is 15, plus 3 is 18. So square root of 18 squared plus 3 times negative 3 is negative 9. Negative 9 squared is 81 squared. And you can do this out, but it comes out to like a little over 20, 20.1 or something like that. Let's say it's meters per second squared. The other part you have to do is find the angle. Well, that should also be easy because you have a sketch. Oh, I just want that angle there. No big deal. That angle is going to be the inverse tan of opposite. That's the AY. That's the negative 9 over, and then adjacent is 3 times 5, 15 plus 3, 18. And so you plug it in and you'll get your angle. It's not a hard thing to do. Okay? All right, last thing to talk about. Why are we adding vectors at all? Quick answer is you need a resultant. If this is, if this is, jumping around, right here. If this is the boat's engine speed, or the thrust from the engine, it's really the water pushing off, and this is the wind pushing the boat another way, if you add them together, this is literally V1 plus V2. This is maybe the thrust velocity, and this could be the wind velocity. V1 plus V2 will give you the resultant velocity. This is where the boat actually goes, the direction it actually goes in. And so here, by adding those, hey, let me not cheat. Circle the start, X the finish, bring that in here, boom. That's where the boat actually goes. That's the resultant velocity. I mean, that's a pretty cool thing. That tells you which way the boat will actually go. And similarly, we might ask, why subtract vectors? Well, let's say this is like your initial velocity, and this is your final velocity. What if you want to know the change in velocity? You have a pretty simple formula. Change in velocity is always final velocity minus initial velocity. And in this case, here's your final velocity. Cool. Here's the initial velocity, but how do you subtract them? And you've seen this, I'm sure, but it's good to think of it as plus negative. So what's the negative of this initial velocity? It's literally opposite direction. So I have to do two operations here to make it happen. I can flip a left, right, and then flipping up, down, and now it's pointing the opposite direction. So now I can do VF plus negative VI. This is now negative VI, and adding vectors we just did follow the same rule we did above. Make them head to tail. All right, circle the start, X to finish. Bring in your resultant. You obviously would have to draw this. And that resultant here represents the change in velocity. Okay, so there's your change in velocity. And I believe that might be it. Woo! Fun. More fun than you can shake a stick at.